Hello there and welcome to this course on regression analysis for healthcare with Python. My name is Valentine and I'll be your instructor. In this course, we'll start learning about the objectives of the learning experience. After that, we'll talk about various concepts in relation to regression analysis as well as Python. This will just generally entail talking about those concepts or getting to understand those concepts from a theoretical perspective. And we'll talk about why we would want to understand and to use those concepts. After that, we'll get into a practice session where we will use the Python programming language to implement regression analysis techniques or those concepts that we will have talked about. We'll share also challenges. So once we have gone through various implementations of the different regression analysis techniques, will give you that opportunity to practice and acquire that skill, that regression analysis skill that we will cover. And that should set you up for now just working on basically regression analysis projects when it comes to using the Python programming in healthcare contexts. So let's get started. By the end of today, we are expected to have achieved these learning outcomes. So we should be able to recall key regression analysis terminologies to accurately communicate findings to healthcare professionals. We should also be able to describe how common regression algorithms work to select the most appropriate method for a given healthcare dataset. We should be able to create regression models to solve healthcare problems such as predicting patient outcomes or optimizing resource allocation. We should also be able to evaluate regression models to ensure their reliability and effectiveness in informing healthcare decision-making processes. So those are the learning outcomes. Some of the audience might also have gone through another workshop on machine learning for healthcare that we've done in the past. And, one of the questions that one would have would be, what's the difference between that course and this course? This course is primarily focused on one area of machine learning, as opposed to the other course, which generally presents to you all the topics entailing machine learning. So for this particular workshop, we'll be focusing on regression analysis techniques. I'm just talking a bit more about why you would use one particular regression analysis technique over the other. In addition, it should also provide you with some more challenges, some more space to be able to just solidify the knowledge and the skill that you got to learn in that other previous workshop or previous course. And if this is your first time, don't worry. This is also a good start. You can also use that machine learning for healthcare course as a wrap it up course. So once you've gone through regression analysis for healthcare with Python, the same case with another upcoming workshop on classification, as well as also on clustering analysis for healthcare, then you could always decide then to now do that particular course. So that's what we expected to have achieved by the end of today's learning experience. So let's get started. So what is regression analysis for healthcare with Python? So this generally would be that process that one would undertake whether you are a health data analyst or healthcare data scientist or healthcare professional who works with data. And you'd undertake this process and you would build what are called regression models or applications that you would train on data, historical data, to make predictions. So generally, this process would involve using what are called regression techniques to create those solutions or to create those models that would help you to predict whether it's patient outcomes or just even be able to identify maybe risk factors or even optimize health processes. The potential of what you're going to be learning today is vast, and it's usually dependent on just different contexts that you're working with. But The idea is that once you have gotten to understand how to perform regression analysis, you have a tool that in any case where you are faced with a problem that involves prediction and you have historical data and you want some sort of intelligent automation, then you can always think about incorporating the skills that you learned today. So in the process of creating these models that we call, these applications that we call models, which we train on historical data, in that process, we usually use what are called algorithms. Algorithms are complex mathematical functions that we can use to create models. And there are tens or hundreds of algorithms that we have at our disposal as data professionals, as well as healthcare professionals. Some of the ones that we are going to be learning about, which we are calling them techniques, regression techniques, are linear regression. That's an algorithm. It's a complex mathematical function that works differently from other regression algorithms. There's decision tree, there's k-nearest neighbors, support vector machines, and random forest. These are just a few of the basic ones that might be appropriate for just basic projects when it comes to regression analysis. However, if you feel like maybe you'd want to further your journey when it comes to regression analysis, we would recommend that you look into other types of regression analysis techniques, which are a bit more advanced. And these ones are usually called ensemble learning algorithms, but now specifically for regression. You can have ones for regression and also ones for classification, but our focus is on regression. So we will go through over just some quick intro on what all these different algorithms entail, and then later onwards, once you have developed a model based off any of these algorithms, then you can decide to focus on maybe one particular algorithm and ensure that you get the most out of it. And that could entail ensuring that you prepare the data in a format that particular model that's based on, the particular algorithm that you've chosen actually is in the right format. Let's say, for example, if you create a model that you're going to use later for prediction, that is based off linear regression, when it comes to preparing data for that model, you would need to think about, do you have, are all the variables or all the columns within your training data set, or the data that you're going to be using to train that model, do they have some sort of normal distribution? Do those particular variables also have a positive relationship with the target variable? That's the variable of interest. So we might be, by the way, talking of some new words, but we'll explain those vocabulary key terms as we continue. But generally, that is something that you would want to do later onwards, once you have determined that you'd want to work with one particular model, or and that would mean, let's say now you prepare data to ensure that it's in that format that the model would want, or would for it to be able to perform even far much more better. And that usually would refer to a field, well, a topic still in data science or data analysis called feature engineering. Or alternatively, instead of you would want to have data, if you want to have a model that performs well, aside from just working on the data, you could also configure the settings of that model, and that involves a process called hyperparameter tuning. That's also a different topic by itself. It's one that one would cover in just a solo workshop, to just be able to fully understand what you need to take into account when you're tuning, or when you are setting those settings with regards to the model that you're going to be working with. So that's just a quick intro into just the different regression algorithms or the techniques that we're going to be going through, and a use case of where regression analysis for healthcare with Python would be, a use case of such would be assuming that maybe you're a healthcare data analyst and you would want to predict maybe patient length, maybe patient length of hospital stay for just the patients that you have within your hospital, then you can create a regression model or a model that uses any of those techniques that we've talked about, and you would train it off historical data that contains maybe demographic factors, medical history of patients, treatment procedures, and it would use its key lessons and from that data set to now be able to make predictions on whether new patients with who've come in, whether they're going to be able to, it will be able to predict the length of stay or hospital stay for those particular patients. And, that can be eye-opening for other business stakeholders or other management stakeholders who would allocate resources for the hospital appropriately. And yeah, so there's the potential of regression analysis is vast, and that's what we are going to be exploring. Something to note also when it comes to regression analysis, as mentioned, it's a process that involves creation of a machine learning model or model. You can just call it a model, but we normally call it a machine learning model. It's that process where we create that model to predict a target variable, to predict a dependent variable. If you come from maybe, if you remember back in high school, we used to have independent variables and a dependent variable X and Y. But the dependent variable would normally be, in this case, where we would want to use regression analysis, that dependent variable would normally be one that is of a continuous nature. So it's usually a continuous variable. It has multiple values that range. Maybe, it could be real numbers, which is zero from it could, and upwards, it could be 0, 100, 300, 400, 1,000, million. So you can think of it as a numerical variable. And on the other hand, on the other side, where you have maybe a class or a category that you want to predict, in such a situation, you would be performing what is called classification analysis. But now, in our case, regression analysis focuses mainly on having that dependent variable being of a continuous, being continuous in nature or numerical in nature. And for example, assuming that we want to create a model that we would want to use to predict maybe hospital stay for new patients, then as we could use this sample data set, that has vital signs, that's temperature, heart rate, blood pressure, etc. We could use this data set to predict the length of stay column, which is on the far right. The length of stay column is numerical in nature, it's continuous in nature. And then, we create a model that's able to predict that kind of a variable. And problems that have that dependent variable, we would then use regression models to create to create solutions to train our models on. So if you use a regression algorithm for such instances. Other examples of target variables or dependent variables when it comes to data science or data analytics, we give the dependent variable the term target. And these are just a few of other variables that might come in handy. Length of hospital stay, readmission rates, medical cost prediction. These are just other continuous variables that we might want to predict when it comes again to working on just different problems. The process of creating a model normally would require you that you have an understanding of various concepts, like what is supervised learning, and supervised learning generally would be a category of machine learning that would involve you being able to train a model. So you're basically supervising it in that process, and then using that model to make predictions on new data. So regression analysis is part of supervised learning, and under supervised learning you would have regression analysis as well as classification analysis. Classification is different from regression in that you have a variable, a target variable that is categorical in nature, where you have maybe values of true or false, maybe, or high, low, or medium. Those are just categories or buckets that you would be predicting. Another concept that you need to learn is that when it comes to the historical data sets that we are going to be using to train the data on, we normally would give the independent variables the term features. So features, when we say features, we would generally be referring to the independent variables, and when we say target, we would be referring to a dependent variable. And these two terms would also be applicable in classification, not just in regression. Something else which hasn't been included in the slide is that when we have independent and dependent variables, and when we are performing training, or we're training a model, we would need to split our data sets into what are called test data sets, and a test data set and a training data set. And the proportion of those data sets can vary, but normally the test data set is usually a smaller data set than the trained data set. And the purpose of a training data set is to teach a model how, or it's to help a model learn about the data itself. And the training data set usually has both the features and the target variable, both values. So while also the same case with the target, with the test data set. But we would use the training data set to train the model. Then later onwards, once we have trained a model, we would decide to take the variables, that's the features for the test variables, and we would ask the model to predict the target, its own target values for the test features. So and then once you get the results of the model, so the predicted target values for the test set, you would compare those values by the model to the original values for the test data set, and you would determine the errors, and as well as also determine other evaluation metrics. So we usually use an evaluation metric. So that's how we also measure how a model performed. We have what are called evaluation metrics, which work differently. And yeah, so we'll also get a bit to learn about that. The whole process of creating a machine learning model starts from, not even from here, it usually starts from business understanding, trying to understand first what the business stakeholders are trying to solve, and you would then resolve to, first of all, coming up with just a list of solutions that would work for the problem that the business stakeholder is facing. And when you realize that, when you have gone through all the solutions and realize that a machine learning model would be the most appropriate solution, after evaluating different factors, then you can then decide now to look for data. Not even look for data, and you can first of all ensure that you set a metric of success, like, assuming that you to create this model, what would be a perfect model be? Would it be a model that has that has an a number in terms of accuracy rate? Then once you've determined that metric of success, then you would look for data for training as well as testing. You would load that data, preview the data. That's now where we have mentioned step one. You clean the data to ensure that also it's in the format that the models would be able to take. If you have a data set that has textual data, you need to convert that data into a numerical representation using various techniques. Then after that, you then split the data that you have into a training and a test set. Then you evaluate the model using various regression analysis evaluation metrics. There are quite a large number of them. We will get to learn about the root mean squares, as well as also the R squared metric. Then once you have a good model, then you can decide to use that model to make predictions with now some new data that you have. This is just a general overview of the entire process of creating a regression model, but you can still be able to further enhance this process by performing what are called feature engineering techniques. So in the process of cleaning and pre-processing the data, you might decide to create new features. You might decide to do what is called feature scaling, which just involves transforming or changing the scale of the data that you have. Maybe, I won't talk so much about that because I can see we are taking too much time in this section, but you can decide to do a whole lot of other techniques. This is just a basic template that you can always follow. All right. When it comes to now I think this is where we now go into just the different regression analysis techniques. We'll just quickly go through the individual regression analysis techniques, talk about what they entail, how they work, as well as some assumptions that we need to take into account when we are working with all of them. But it's important to understand that when you're initially creating a machine learning model, the best approach, or not they could be a best approach, but this approach that many people find, I wouldn't say it's the best one, but the approach that many people usually find useful is one that involves creating models for all the different techniques using a clean data set, a data set that has numerical data, doesn't have outliers, etc. Or sometimes it could have outliers if they are genuine, but it doesn't have missing values. You handle the missing values, etc. So once you have prepared a data set, you can decide to create a linear regression algorithm model based off a linear regression algorithm. You can decide to create a k-nearest neighbor model, decision tree model. And then once you have created all the models, you can then test, you train them, test, then you check their accuracy scores. Once you have, once you've checked the accuracy scores, you might decide to go you might decide to pick the one that performs well with the data set as it is, then enhance that particular model by performing feature engineering or hyperparameter tuning. And then now looking at of course, maybe in this situation, maybe with this data set, linear regression performs the best. So you would decide to now go further and ensure the data set in the right format with regards to maybe to linear regression, and look at, all right, linear regression has the following assumptions. It assumes that there's a linear relationship between the independent and dependent variables. Then you would now go back to the data set that you use for training. Actually, before that, the original data set, then you would ensure that all the variables that you're working with are dependent, that they have a linear relationship between, linear relationship with also the dependent variable. And if they don't, you could decide to drop them, or delete them, or not use them at all in your analysis, because now in such a situation, you want to enhance the performance of the linear regression model, which is the one that you're working with. That's usually an entire process, but now we're going to just go through each and every algorithm, and then we can be able to just get a good in-depth perspective of how those algorithms work and when to use them. And a decision on whether to use one or the other will just be dependent on your case. So starting off linear regression, it's usually a type of an algorithm that helps us to be able to create models that assume that there's a relationship between the dependent variable, that's the target variable, and the independent variable. So it usually assumes that there's some sort of positive relationship. Like, for example, as the values of one independent variable increase, the values of the dependent variable, the target variable, also increases. So it assumes that each and every independent variable has such kind of a relationship. It could be negative, like on a positive, whether maybe the values decrease while the other one increases, or decrease and the other one increases. So that's usually the basic assumption of linear regression. and we would normally use it when, say, again, for example, we also do not, actually, I've already talked about it. We would use it when there's a linear relationship. And in some other situations, it's normally used in there are many cases, I think, in banking. So because of its interpretability, you can be able to interpret how a model arrived at a result easier, much more easier than if you're able to use maybe another complex model. The assumptions that this particular model tends to have is that, aside from that linear relationship assumption, is that it also assumes that there's little or to no multicollinearity. That means the independent variables do not have any correlations, just as it would have to have a correlation with or have a positive relationship with the target variable. It assumes that you do not have those relationships in between the independent variables, and if there are, you need again to make a decision on the next thing, but that would also impact how the model performs. It also assumes that there are no outliers or influential observations, so you would need to ensure that the data set is there are no outliers generally. If there are, then you could decide to do something to the outliers. You could decide maybe to, based on domain knowledge of the the context that you're working with, whether to retain them or not. But if you decide to retain them, I would highly advise, or it's usually highly advisable, to use a different model that works well with outliers instead of linear regression. The other type of algorithm that you'll get to work with is usually called a k-nearest neighbor, and this type of algorithm it's a distance-based algorithm. So what happens is that in the training data, when it's learning from the training data, what it does is that it learns the positions of the data within some sort of Cartesian plane. You can think of it as that. And when it's making new predictions, you give it some new predictions, so it tries to put, I'm trying to look for that word. It tries to take this new record that you want to make a prediction for, and it compares it with the positions of the rest of the points that it learned from. So it tends to look at, all right, for this new record, it's much more closer to maybe three of these records in terms of distance. It's much more closer to that, and then it would get an average score of those particular target values and use that as the value for now that new record. And this particular algorithm, it usually assumes, when you create a model based on this algorithm, that model assumes that the attributes used to measure similarity, they are correctly scaled. So in the situation where you have columns, the attributes are just the columns of variables, you have variables that have large values, then it means that in such a situation you'd need to scale your data set. There's a technique that's called standard scalar technique you can use. It's also normalization. So you would need to ensure that your data set is normalized so that you don't have a significant the significance of those large data set does not impact how the model performs greatly. So generally, it assumes that you have scaled your data, the data that you're working with, before using this particular model. There's support vector regressor, which generally would take training data, and then it would map it, put them in a Cartesian plane. But generally, we say it maps that data into higher dimensional space and creates a a line called hyperplane that usually gives us the most space between the data points and the line itself. I won't go so much into the details. There's a whole lot of mathematics involved. And, that is how it does it. So once it has been trained to be able to find that hyperplane, then it can be able to make predictions on new records using the same approach that you give it to. A few assumptions, actually, too. This particular type of model tends to work well whenever you have lots of variables, or when you're working with data sets that have high dimensional space. Or usually you say when you have lots of variables within your data set, maybe 30, 40, 50, 100, and you have fewer, not so much fewer like records, but when you have much more records, much more variables in your data set, then you can use this particular type of algorithm, type of model. But again, I wouldn't say you can use it immediately. I would say it usually performs well when you have data sets that have many not categorical, but many variables generally. It also assumes that the data is actually not linear. It's usually non-linear. So I think, well, I'm not really sure about that. I would have to check for that. I'm trying to remember that. Yes, I think when you also don't have much noise, but for linear, because SVR also has, it usually uses what are called Kano functions that you can use to describe how your data set is, or the data set that you're working is. If there are lots of positive linear relationships, then you can use a Kano function called linear. Otherwise, you can use what is called RBF. So a different type of Kano function. So it uses what are called also Kano functions to be able to learn from data and be able to make predictions. But most of the times usually works well, especially when you have data sets that have many variables generally. Decision trees, on the other hand, are, these models tend to work with the ones that are based on decision tree algorithm. They normally work by partitioning the data into smaller subsets based on the values of input features, and the approach that they use on how they split the data into just those different subsets is usually through the use of either Gini impurity or entropy. These are just approaches that the decision tree these decision tree models tend to use. And the model itself, the decision tree model itself, tends to work best when maybe you have a lot of categorical variables, as well as also maybe linear and non-linear. Like you also don't have independent variables having a positive relationship with the target variable. Then you can use them. And they can work with, again, both numerical and categorical data. Random forest is just it's just based off decision trees, so it's usually what is called an ensemble learning model. So a random forest would be based off a multiple decision trees. So it's, if you want to decide, maybe if you realize maybe a decision tree does not give you the best, or even it works well, but you might want to further enhance a decision tree, instead of either performing hyperparameter tuning or feature engineering, you might decide to use multiple decision trees, and that's where random forest can come in, and it will just implement the same. It will take into consideration of what decision trees also take into consideration. The only thing here is that random forests usually computationally expensive because you're using more decision trees. That means you would end up consuming more computing resources. It's also sensitive to hyperparameters, such as number of trees and number of features that you would set. So these are just settings. And in many cases, when you have many random forests, the ability to interpret them is usually quite complex. So sometimes you just may go for just one decision tree if that works well for you. All right, so at this particular point, we are going to move on to a practice work. Then we are going to implement the different algorithms we've talked about, and then we can call it a workshop. So let's get started first by visiting the link that we have shared in the chat. There's a resources link. Click on that link. It should take you to a page that allows you to download a sample resource for this workshop. But if you're an Afterwork member, you could always consider becoming, if you're an Afterwork member, you will be redirected. Once you've signed in, you will be redirected to a practice resource page, and you'll get access to this notebook. So the first thing that you need to do once you get to this notebook is to connect the notebook. Well, not even connect. You could decide to connect it if you don't want to save any changes, but you could first of all go to File, then save a copy in Drive to save the notebook in Drive. It will open a new tab, and then you can use that new tab and close this one. So you can use a copy, and that copy will be saved on Google Drive. By the way, if you feel like we are too fast when going through content, you could always pause the video, rewind a bit, as well as also ask questions in the comment section too. So so let's get started. Once you have done that, the next thing that you need to do is to connect the notebook. So you can click on connect. I'll use the practice resource instead of the sample. It will take a few seconds. Afterwork members, you also have a solution notebook that you could always use to verify your solution. To take a few seconds, let's see what's happening. All right, it has connected. You'll see a check, and then we can go to the next thing. So first of all, we're going to import just the basic standard data manipulation in scientific libraries. That's pandas and NumPy. Run that. If you get this, don't worry about it. Just say run anyway. All right, once you have done that, we'll start off learning about how to implement regression, linear regression. So assuming that already we have identified that we want to use, we want to create a machine learning model, and we have a data set to use for training. So let's first of all import it. This is the data set that we're going to use. It has patient ID, age, gender, weight, diagnosis. This is the variable of interest, length of stay. We have medication cost, total cost, insurance coverage. So what we have here is just historical data about patients. This is just normalized data. It's not real data. This is data that we've created for the purpose of learning. Once you have this data set, what you can do is to, now we're going to clean to ensure that the data set is in the right format. Or alternatively, we might decide to just work with the variables that we would want. We would want to work with age, gender, weight. We might even decide not to work with gender if we don't want to pre-process. But it's important to pre-process, so that pre-processing just means ensuring the data is in the right shape, like formatting this into numerical equivalent. So age, gender, weight, height, diagnosis, length of stay, medication cost. So we are going to create features, independent variables, which we are going to select here: age, weight, height, medication cost, and total cost. Our focus here is not really data pre-processing. That's why we're just selecting these ones, but you could always select those other ones. But we will also showcase how to just perform data pre-processing for those other models. So this is just a quick way of just learning. So once we have created our, we selected our independent variables and saved them in X, capital X, and Y. Y is just now the length of stay, which is the target. We then decide to split the two data sets into test and training tests. So we will have 4 data sets. We'll have 2 from the independent variables and 2 from the dependent variables. So you'll have two data set, one X train and X test from you'll have one X train. So that's the training data set. You'll have a training data set, actually 2 training data sets from here, and also 2 test sets from here. Did I make the sense? No. All right, let me go back again. So you'll have 4 data sets. 2 of them will come from X and 2 of them will come from Y. X has independent variables. That's the features. And Y has the dependent variables. We will split these 2 tests based on some criteria. We want 20% of the data sets of this data set, or 20% of the values of length of stay to be for the test set and 80% for the training. We want 20% of the X to be for test and 80% for training. If you have been confused, you could always just rewind a bit and you can always catch up quickly. Then we just used how to split. To make that split, we used this function, train test split from model selection module from sklearn. And then we created those different data sets. These are just 4 variables. That's how you can create multiple variables in Python. We use the function itself. This train test split function usually takes the 2 data sets, and we define our proportion, and also we set random state so that if someone else wants to recreate the same data set because the data set is created randomly, so if you want to get the same records or produce the same records for X train or the 4 data sets, then you have this is 42. If I set it as 1, then the other person who gets this code, like you'd also need to have this as 1. If you change it, you'll get different records. Then we import linear regression algorithm. We create an instance or an object. And then this is like just creating now the model itself. Then we train it using the fit method. Then we evaluate. We evaluate in a model using just various metrics. The common ones in regression mainly are root mean square error. And root mean square error, how you interpret it is that values closer to 0 normally would mean that the model performed well, and values greater than, like really far off from 0 are performing poorly. But again, that usually it would mean the model performs poorly. But it would be that you can have multiple models and compare the RMSE scores, or root mean square error scores, and identify which one has the value that's closest to 0 and consider that the one is the one that performs well. Or alternatively, if you're working with one model like this, and normally we would use the average of length of stay. So we would get the average of length of stay. So assuming we had 5, and the root mean square error would end up being maybe 1. Normally we would say that to have a linear regression model that performs well, the root mean square error has to be less than 10% of the average of length of stay. Again, that's also an acceptable sort of error range. But if you have more of that, then the model might not be predicting accurately. R squared just means how well your model fits the data. And values of R squared usually range from 0 to 1. For R root mean square error, they usually don't have a upper bound. They usually start from 0 to upwards. But for R squared, it's usually 0 to 1. And what we normally look for when it comes to R squared is just a value that's closer to 1. So yeah, let's run this to perform the process of cleaning, preparing, data modeling, which just generally means creating the model as well as training it and then evaluating it. So here we can see that we have root mean square of 0.16, and which is okay. But again, we would need to check with the average. We can just say describe, we can do data.describe to get the numerical statistical information for the numerical variables. So that would give us, so length of stay, you can see here, average of length of stay 6.7, 10% of 6.7 would be like 0. Should be like 0.67. So 0.67, which this 0.1 is quite less than 0.67, which we can say the model actually performs well. And we also check another evaluation metric, and we see that we have a good evaluation metric because it's closer to 1, which is good. We can even further make this model perform well by simply, using these other, maybe performing feature engineering, which would involve converting these values, etc. But again, that isn't also guaranteed. You would also need to recreate the model and check for its performance. So once you have done this, you can now, once you have a good model that performs well, you can use it to make it a new, some new prediction. So for this new patient, what would be the average, or what would be their length of stay? That's what we're doing here. We're creating a new data frame for the records, for their records. So they come in and they have this information, and then the prediction. We use the predict function to make that prediction. And we have 6.7. 6.7 is the average stay. 6.7 could be actually 7 days. Yeah, 7 days for that patient. All right, at this particular point, pause the video, work on the challenge. If you're an Afterwork member, you could always preview the solution afterwards. So the challenge is here. This is the challenge. All right, K nearest neighbors. I won't repeat explaining the different parts. I think I've done that. So we talked about having K nearest neighbors. You would need to take into account, we need to scale our data before training. So we have loaded the data set. This is hospitals data, the many hospitals. We want to create a model that predicts net profit, which technically may not necessarily be, well, it could net profit, but again, net profit can, it's not the best. It's not the best variable, numerical variable, but for the sake of learning, let's just learn how to talk about it. I've just said net profit may not be the best because net profit is just the difference between total revenue minus total expenses. I should have seen that, but yeah, let's just learn how to implement it. But we could use the same model also for this particular case, for the linear regression case. So let's select the data that we want, assuming net profit is our variable that we want. Then we would split the test into the training and test sets. Then we perform scaling. So in our case here, we would ensure that the data is in a format that's closely, that's close to it's scaled. It's in a format that ensures that the bigger values do not have a significant effect, especially for something like these two. So let's run this. We've already run that. I've forgotten. Then we'll do that. Then we will, here we also import our algorithm. Then we we create our model. And we want this model to only take 3 neighbors. This is important. You always need to give this value to K nearest neighbor. It will take into consideration 3 neighbors or 3 existing records when it's making predictions. So it would take those values, their values, and be able to use them. And then don't worry about this, it's just because this was the last one. And then we check the evaluation metrics. And we can see here root, the R squared is okay. but the root mean square is quite large, so we would need to investigate further by checking the net profit. What's the average of maybe the net profit, which you could do by just saying data.describe, and you check for net profit, what would be the average. So this is what we have. Mean is 118. 10% of that is 11,000, which is less than 10%, which is okay. This one also performs well. It's okay. All right. And then we can use it to make new predictions. We check, we have our new data. Then we make a prediction. This is the prediction for that. All right, pause the video and then work on the challenge. Just note that here we are not really so much focused on that context bit. I overlooked that in setting up of that question, but just note that you're learning how to implement k-nearest in such a situation. Let's now go to decision trees. We'll load this data set. We want to create a decision tree model. And we are going to, by the way, for k-nearest, we used a regressor. It's k-nearest neighbors regressor. The same case we are going to use in our case decision tree regressor. For classification, you actually have the same models. You tend to use what are called classifier. So you'll see a model called decision tree classifier and k-nearest neighbor classifier, etc. Right. So let's for decision tree regressor. We also do the same thing, but we're not scaling. Doesn't matter in our situation here. So we would just select the target and features, perform, split our data set in training and tests. Then here we instantiate our model. Then we evaluate the model. And we can see that, and this is 391,000. Again, you could always check the performance of, you can check how it performed relative to the average of the annual revenue, which is also here. I should have considered something else, but here it's okay because we don't have that data. So annual revenue, you check how it performed in regards to also annual revenue. Yeah, so use it to make a new prediction. It's 2 million. All right, pause the video, work on the challenge. Random forest, let's learn how to work with random forests. Something that we will do different here. So instead, initially we were just selecting the records that we had here without converting maybe these locations into equivalent, or the categorical variables into equivalent numerical representations. So in our case here, we're going to be using a different technique of that conversion, so called one-hot encoding. So we will apply it to our entire data set instead of just going through individual columns. We'll apply it to our entire data set, and it will ensure that we have records that our model can take. Our model can take numerical records, and in any case that where we have maybe true or false as the value of representations, it will just assume true as 1 and false as 0. So let me just show you that here. We're just cleaning, we're dropping missing values. We also don't want to work with total cost and hospital ID. Total cost is now for the target. That's what we're interested in. We convert our categorical variables, and then we can preview those categorical variables. So, which is what you can see here. So larger variable. So true or false will be treated as 0. True will be 1, false will be 0. And then we can now use a random forest regressor we can train it, and then we can check its evaluation metric. So for random forest, you can see we have the RS of MSC is 417. the R squared is 0.9, which is closer to 0. So which is fairly okay. But again, mentioned, you could always verify that with total cost, the average total cost, and see how it fares. Pause the video and then work on the challenge. All right, moving on, support vector regressor. So we're going to load this. In our case over here now, we are going to do like thorough data processing, but don't worry so much about this. Is just a process of cleaning. Assuming this is our data set, it's quite dirty. Like here we have percentages, we need to do something with them. We need to convert supplier location and also work with expiration date. We can get maybe year values, like a month and day values, and have them in separate columns. So we're going to do that as well. We're going to do quick data cleaning, which we do here. I won't go through over all of this, but here, instead of doing, in the previous example, we did one hot encoding, but here we just decided to use another method called label encoding that will just simply replace the values of the categorical variables with just numerical equivalent. So once we have cleaned our data, we'll get something that looks like what you're going to be seeing here. And then, just create our feature and target variables. And we don't want to work with discount and medication. We for the features. But here now we just use our SVR, we train it, we set the kernel to RBF once we have determined like we don't have lots of linear relationships in our data set, and then we can evaluate it. All right, and here you can see there's a minus. This implies that this model performed badly for various reasons. There could be outliers within our data set, or it did what is called fitting, or there are quite a number of reasons, which would mean this data set isn't the best data set or this model isn't the best data set. This is the best model to use with this data set because of various factors that the categorical the data set poses. So we would want to use maybe a different model in such a situation. So once we get here, we did not even do a prediction for this particular case. All right, pause the video and then work on the challenge, and then we can wrap up the session. All right, so that's it. That's it with regards to this course. I hope you are able to quickly get to experience a bit more with the regression algorithms, and you can, create basically a model that can be used to make predictions. We are actually going to be starting some series on just being able to create we're going to be creating just different applications that you can be able to see that would help you just visualize the entire process of creating a model and using it in production. But generally, as the next steps, we would advise that now you're looking to classification analysis or clustering analysis, which should also help you to just be better at just creating models using machine learning concepts for just different situations. You can do projects as well. We have a regression analysis with Python course. It doesn't have any context. You can think about how you can maybe even become an afterwork member and get to explore that project that we have. And if you want feedback, you could always send it to us for just feedback. But again, we also have provided solution notebook. All the best in your learning journey, and I hope to see you in the next workshop, in the next course. And if you liked the whole experience and you'd want to tell us that we are doing something that you'd want to see, or we are doing something that's good, you can leave us a thumbs up on YouTube. And if you'd want to be informed when we post such future videos, be sure to subscribe, and you'll get notified when we post future courses. All the best in your learning journey, and see you next time.